14 billion years ago, something beyond imagination occurred. Everything space, time, matter and energy erupted from a point smaller than the tip of a pin. We call that event the Big Bang, but the truth is far stranger than the name suggests. What if that colossal eruption wasn't the true beginning? What if it was just one beat in a rhythm that has been pulsing forever? Some of the world's most brilliant physicists, including Nobel Prize winners, now believe our universe might not be the first. Before our cosmos exploded into being, another might have existed, and before that yet another, in an endless sequence of creation and dissolution. Traces of that ancient reality may still linger in the heavens today, mysterious patterns of heat and light whispering from the edge of time, suggesting that the cosmos has died and been reborn more than once. To understand how radical this idea is, imagine compressing everything that exists, the stars, galaxies, atoms and energy, into a region smaller than a single atom. That infinitesimal point is known as the singularity, the supposed cradle of the universe. It's where all known laws of physics cease to function. When scientists try to describe it using mathematics, their equations explode into infinities, infinite temperature, infinite density, infinite curvature of space. Infinities in physics aren't just large numbers, they're signals of failure. They tell us that something in our understanding is profoundly incomplete. The singularity is the cosmic red flag warning that our picture of reality breaks down at the very moment we need it most. Albert Einstein's general relativity, the magnificent theory that explains gravity and the geometry of space-time, performs flawlessly almost everywhere, from predicting black holes to explaining the time corrections in GPS satellites, yet at the singularity, it collapses entirely. The math that governs planets and galaxies cannot describe the instant when the universe supposedly began. This is known as the singularity problem, and it sits like a thorn in the heart of cosmology. If our best theory of gravity fails at the moment of creation, then we are missing something essential about how the universe actually works. For decades, physicists have wrestled with this paradox. Stephen Hawking devoted much of his life to probing it. Roger Penrose earned a Nobel Prize for demonstrating that singularities are inevitable within Einstein's equations. Yet both men ultimately wondered if the singularity was ever real at all. Could it be that our universe never emerged from nothing, but from something deeper and older, a process rather than an instant? Think about what that implies. Every atom in your body, every ray of sunlight, every galaxy scattered across the night sky, all of it, according to conventional theory, sprang from a mathematical impossibility, from a point where logic itself disintegrates. That isn't an explanation, it's an admission of ignorance wrapped in equations. The mystery deepens when quantum mechanics enters the story. Quantum physics governs the realm of the very small, where particles behave like waves and uncertainty rules everything. Its rules clash violently with those of general relativity. At the tiny scales of the Big Bang, quantum effects should dominate, yet we have no working theory that unites quantum mechanics with gravity. We're blind to the crucial first moments of existence. Some scientists simply declare that the singularity marks the beginning of time itself, that before has no meaning. Time began ticking with the bang, and whatever preceded it is forever beyond reach. But for many thinkers, that explanation feels like surrender, like closing the case because the evidence is missing. If the laws of nature break down at the moment of creation, perhaps it's the laws that need rewriting. Over the past few decades, daring new ideas have emerged, proposing that the Big Bang wasn't a beginning at all, but a transition, a transformation of an older cosmos into the one we inhabit. These theories suggest the universe may be cyclical, expanding, fading, and being reborn in endless succession. Among their champions is Roger Penrose, who argues that the cosmos undergoes infinite cycles of death and rebirth, each separated by a phase so extreme that it erases all traces of the previous era. According to this vision, our universe is merely one chapter in a never-ending story written across eons. What was once seen as an ultimate beginning may in fact be just a continuation, and the evidence for this audacious claim may already be written across the sky. Tiny irregularities in the cosmic background radiation, the faint afterglow of the Big Bang, could be echoes of a universe that existed before ours. They are not easy to detect, but if confirmed, They would prove that the Big Bang was not the birth of everything, only the latest heartbeat of an eternal cosmos. The deeper we look into the universe, the more it resists the idea of a simple beginning. Each discovery peels away another layer of certainty, revealing that what we thought was the start of time might instead be part of an infinite rhythm, a cosmic pulse that never truly began and will never truly end. Our journey into this mystery starts by confronting the uncomfortable truth that our most trusted equations fail when pushed to their limits. To uncover what really happened 14 billion years ago, we must look beyond the Big Bang itself and ask a question once thought impossible. What existed before the beginning? When scientists peer backward in time using the laws of physics, the equations of general relativity guide them toward a single inevitable destination, the singularity. It's a place where density and temperature reach infinity, where space and time themselves shrink to nothing, and where the rules that describe everything else in the cosmos simply stop working. Yet, despite its name, the singularity isn't really a place in space. It's a boundary of understanding, a horizon of knowledge beyond which our familiar mathematics and intuition fail. We call it the beginning, but it might instead be the point at which our theories surrender. The singularity problem sits at the core of cosmology like a paradox we cannot ignore. Imagine trying to calculate what happens as you rewind the universe. Galaxies move closer together, temperatures rise, matter becomes more compressed. Push further and atoms disintegrate into nuclei and particles. Radiation dominates, gravity intensifies, and all distances shrink. In the equations of Einstein's relativity, this compression continues endlessly until volume reaches zero and density becomes infinite. That infinity is not a real physical object. It's a mathematical alarm bell telling us that something about the picture is wrong. No real quantity in nature should ever be infinite. Infinity means our tools are broken. For decades, physicists tried to tame the singularity using clever modifications, but none resolved the core issue. The problem stems from the fact that general relativity and quantum mechanics, our two greatest theories, are incompatible. Einstein's relativity describes the universe on large scales, from planets to galaxies, treating space-time as a smooth fabric that can bend and stretch. Quantum mechanics, on the other hand, rules the microscopic world, where uncertainty, probability, and discrete particles dominate. When the universe is compressed into a region smaller than an atom, both sets of laws must apply, but they contradict each other. Relativity insists on continuous geometry. Quantum theory demands granularity and fluctuations. When they collide, chaos erupts in the math. It's as if we're trying to merge two languages that share no common grammar. The singularity emerges from this clash. In the early 20th century, cosmologists like Alexander Friedmann and Georges Lemaître, working with Einstein's equations, discovered that an expanding universe must have originated from a highly dense state. Observations by Edwin Hubble later confirmed the expansion, strengthening the idea of a beginning. But if we extrapolate that expansion backward too far, the density becomes infinite, a nonsensical conclusion. That infinity means the theory can't tell us what actually happened at T0. Physicists realized that to truly understand the birth of the cosmos, they would need a theory that unifies quantum mechanics and gravity, a quantum theory of gravity. Without it, the earliest moment remains forever hidden behind a veil of mathematical breakdown. Stephen Hawking and Roger Penrose explored this problem deeply in the 1960s and 70s. Using powerful theorems, they proved that under very general conditions, singularities are unavoidable in Einstein's framework. Gravity itself ensures that if a universe expands as ours does, it must have once been squeezed to a point of infinite curvature. Their work was both brilliant and unsettling. It showed that general relativity predicts its own demise. The theory that explains the fabric of space-time also tells us that the fabric tears at the beginning, creating a contradiction that no amount of clever algebra can patch. This led to one of the greatest quests in modern science, to find the laws that replace the singularity, the deeper rules that govern reality when space and time lose their meaning. Over the decades, many contenders emerged. Some proposed that quantum effects could smear out the singularity, replacing it with a smooth transition or bounce. Others imagined that what we call the Big Bang might have been the collision of higher dimensional objects, or the decay of a previous vacuum state. Each theory offers a way to avoid the impossible infinities and restore meaning to the universe's origin. But beneath them all lies the same conviction. The singularity is not a real thing, only a shadow cast by incomplete knowledge. It's a signpost pointing to new physics, not an endpoint of creation. The singularity problem is not confined to the Big Bang alone. It also appears inside black holes, where gravity crushes matter beyond recognition and light cannot escape. There too, the equations predict infinite curvature, suggesting another breakdown of the known laws. The connection between black holes and the Big Bang is profound. Both mark regions where time, space, and energy reach extremes beyond comprehension. Some physicists even suspect that understanding one will illuminate the other, that perhaps the universe itself was born from something akin to a black hole explosion in a higher dimension. Whatever the truth, one thing is clear. The singularity problem tells us we've reached the edge of current knowledge. It's the line between what physics can describe and what lies beyond, a boundary every great scientific revolution seeks to cross. To solve it, we must invent a language capable of merging the vast with the tiny, the cosmic with the quantum. The journey past the singularity is not just a scientific challenge, it's a philosophical one. It forces us to question the very concept of beginnings and endings, of cause and effect, of time itself. If the universe did not start at a singular point, then perhaps there was no first moment, no true creation. Instead, reality might be part of an eternal process, an unending cycle of transformation governed by principles we have only begun to glimpse. The singularity problem, far from being a dead end, is a doorway. On the other side may lie the next revolution in our understanding of existence, the discovery of what truly happened before the beginning of time. Albert Einstein's theory of general relativity stands as one of the greatest achievements in human thought, a revelation that space and time are not passive backgrounds but dynamic, flexible entities woven together into a single fabric. According to Einstein, massive objects like stars and planets warp this fabric, creating what we experience as gravity. Space-time tells matter how to move, and matter tells space-time how to curve. This elegant idea reshaped the cosmos from a static arena into a living geometry in motion. It predicted black holes, gravitational waves, and the bending of light by stars, phenomena later confirmed with stunning precision. Relativity transformed our understanding of the universe from a clockwork of forces into a symphony of geometry. Yet within its brilliance lies a fatal flaw. When pushed to its limits, general relativity destroys itself. The very equations that describe the curvature of space-time predict their own breakdown at the beginning of the universe. That contradiction sits at the heart of Einstein's greatest failure, one he himself never fully resolved. Einstein originally resisted the idea that the universe could change at all. When he first applied his equations to the cosmos in 1917, they suggested an unstable universe that should either expand or collapse. Unable to accept such a dynamic reality, he introduced a cosmological constant, a fudge factor designed to hold the universe in static balance. Later, when Hubble discovered that galaxies were receding from each other, Einstein abandoned the constant, reportedly calling it his biggest blunder. But history would prove that blunder prophetic because the cosmological constant returned decades later as the mysterious force we now call dark energy. Despite this, Einstein's equations became the foundation for modern cosmology, explaining not just planetary motion, but the evolution of the entire universe. They described how matter curves space, how energy distorts time, and how light follows the geometry carved by mass. With them, physicists could model the cosmos from the first microseconds after the Big Bang to the vast structures we see today. The success was intoxicating. Every observation seemed to confirm the theory's accuracy, from the precession of Mercury's orbit to the gravitational lensing of distant galaxies. Even the detection of gravitational waves a century later echoed Einstein's predictions with near-perfect fidelity. Yet beneath this triumph lurked a paradox Einstein himself sensed but could not solve. His equations worked beautifully everywhere except at the beginning. When applied to the entire universe, they pointed to an origin of infinite density, a singularity. The same mathematics that revealed the grandeur of curved space-time also foretold its collapse into meaninglessness. Einstein distrusted singularities. He believed nature would never allow such infinities to exist, that some deeper law must intervene. He even doubted black holes, calling them mere mathematical curiosities. But observations proved otherwise. Black holes are real, and so perhaps are the singularities they contain. That realization forced physicists to confront a painful truth. Einstein's theory, as magnificent as it is, cannot describe the full story of the cosmos. To truly understand creation, one must go beyond Einstein. Still, his influence looms over every attempt to do so. Quantum gravity, string theory, loop theory, all are built on the foundation he laid. Relativity taught us that gravity is geometry, that the universe is not a stage but a participant. It connected space and time into a continuum where nothing can exceed the speed of light, where motion and rest are relative, and where energy and mass are two faces of the same coin. But it also sealed its own limits by refusing to quantize that geometry. Einstein famously disliked quantum mechanics, calling its probabilistic nature God playing dice. Yet it's precisely that randomness that dominates the universe's smallest scales. When space-time itself becomes microscopic, the quantum must rule. Einstein's refusal to accept that chaos was both his moral strength and his scientific blind spot. He sought a universe governed by harmony, by deterministic laws of elegance and simplicity. But the universe, as modern physics reveals, is stranger and more uncertain than even he imagined. His equations bend beautifully until they encounter the singularity, where they collapse into nonsense. It's as if the language he invented runs out of words just when the story becomes most important. And yet, even in failure, his theory whispers clues to the next revolution. The curvature of space-time hints that gravity might be an emergent phenomenon, perhaps arising from quantum information or microscopic structure. The cosmological constant, once dismissed, may point toward the energy of the vacuum itself, a clue to the mysterious force driving cosmic expansion. Einstein's triumph was to give us the grammar of the cosmos. His failure was to discover that grammar's limits. But those limits are not dead ends, they are invitations. The breakdown of relativity at the singularity tells us that the laws we know are approximations of something deeper, something that unites the smooth geometry of space with the jittering dance of quantum fields. Einstein's dream of a unified theory may yet be realized, not by rejecting his ideas but by transcending them. The irony is cosmic. The man who refused to believe in a dynamic universe gave us the tools to discover its birth and evolution. The physicist who rejected quantum mechanics paved the way for its marriage with gravity. His greatest failure is also his greatest gift, a challenge passed to future generations to complete what he began. The story of the singularity is therefore not just the breakdown of equations, but the echo of Einstein's unfinished symphony. To understand what came before the Big Bang, we must find the harmony between the continuous and the discrete, the certain and the uncertain. Only then can we step beyond Einstein's horizon and glimpse the true origin of the universe he helped reveal. If Einstein's general relativity describes the grand stage of the cosmos, then quantum mechanics governs the flickering chaos of the microscopic world. These two theories are both masterpieces, yet they speak entirely different languages. Relativity sees the universe as a smooth, continuous fabric, where everything follows deterministic rules. Quantum mechanics, on the other hand, paints a universe of probabilities, uncertainty and randomness, where particles blur into waves and events have no definite outcome until observed. Each theory has been tested to astonishing precision, yet when they meet, when the very small collides with the very massive, they erupt in contradiction. This clash is not just a mathematical problem, it's a philosophical one. It strikes at the heart of how reality itself works. Imagine shrinking down to the quantum realm. There, electrons do not orbit like tiny planets. They exist in clouds of possibility, their exact positions unknowable. Particles can tunnel through barriers, entangle across vast distances, and appear in two states at once. Time and space lose their ordinary meaning. The certainty of the classical world dissolves into shimmering probability. Meanwhile, general relativity insists that mass and energy curve space-time smoothly, creating the gravity that holds the universe together. The equations of Einstein's theory describe planets orbiting stars and galaxies bending light with graceful precision. But if we try to apply those same equations to something incredibly small like the moment of the Big Bang or the center of a black hole, the math explodes into infinities. Gravity, when pushed to quantum scales, refuses to behave. Conversely, when we try to apply quantum rules to the universe as a whole, the framework collapses. Probabilities make no sense when there's nothing outside the system to observe it. Each theory works perfectly in its own domain, but fails catastrophically in the other. It's as if nature runs two operating systems that cannot communicate. This incompatibility is the deepest rift in modern science. The universe cannot obey two contradictory sets of laws. There must be a deeper, unified description that contains both as special cases. Finding that synthesis, a theory of quantum gravity, is one of the most ambitious quests in physics. The problem becomes most acute at the Big Bang, where the universe was both unimaginably dense and infinitesimally small. To describe that instant, we need both gravity and quantum mechanics to work together, but their equations collide head-on. In relativity, space-time is continuous. In quantum theory, it flickers with uncertainty. When combined, those fluctuations cause gravity to behave wildly, curving space to infinity in all directions. The result is mathematical nonsense proof that our understanding is incomplete. Quantum mechanics was born in the early 20th century out of necessity. Classical physics could not explain phenomena like black-body radiation or the photoelectric effect. Pioneers such as Planck, Bohr and Schrödinger revealed that energy comes in discrete packets quanta and that particles obey strange probabilistic laws. Einstein himself helped create this revolution by explaining light as both a particle and a wave. Yet he later grew uneasy with what it implied. God does not play dice, he famously said, rejecting the idea that chance ruled the universe. But experiments have consistently proven that quantum mechanics works. Its predictions are among the most accurate in all of science. The entire digital world from transistors to lasers depends on its principles. Still, when physicists attempt to quantize gravity, something resists. The mathematical tools that work for the electromagnetic or nuclear forces fail for gravity because gravity shapes the very fabric in which those forces operate. In quantum field theory, particles live in space-time. In general relativity, space-time itself is the actor. When we try to treat space-time as another field, it disintegrates under its own fluctuations. It's like trying to stand on a rug while pulling it out from under your feet. The failure of these two giants to reconcile has given rise to some of the most imaginative ideas in science. String theory proposes that everything, including gravity, arises from tiny vibrating loops of energy existing in multiple dimensions. Loop quantum gravity suggests that space itself is made of discrete atoms of geometry, woven together into a quantum fabric. Others imagine that gravity is not a fundamental force at all but an emergent property of information, like temperature arising from the motion of molecules. Each theory tries to bridge the chasm between the continuous and the quantum, between certainty and probability. The stakes are enormous. Without this unification, we can't truly understand the first moments of the universe, the heart of black holes, or even the ultimate fate of reality. The clash between relativity and quantum mechanics is not just about equations, it's about truth. Relativity gives us elegance and determinism. Quantum theory gives us randomness and ambiguity. One says the universe is smooth and predictable, the other says it is jagged and uncertain. Yet both are right in their own ways, describing two sides of the same cosmic coin. Somewhere beyond our current reach lies the theory that fuses them, a framework that explains how the universe can be both continuous and discrete, ordered and chaotic. Until we find it, physics remains divided between two worlds, the vast and the tiny, the serene and the unpredictable, Einstein's continuum and Heisenberg's uncertainty. The quest to unite them is more than a scientific pursuit. It's a search for coherence in the deepest sense, a desire to understand whether the universe is built on chance or on purpose, on chaos or on harmony. In that struggle lies the key to decoding not just the laws of nature, but the nature of existence itself. For decades, the Big Bang stood as the unquestioned origin story of everything, the cosmic explosion that created all space, time, matter, and energy. But as our understanding deepened, cracks began to appear in that narrative. The more we studied the earliest moments of the universe, the more it seemed that the Big Bang might not have been a beginning at all, but a transition. The question, What happened before the Big Bang, once dismissed as meaningless, has become one of the most profound puzzles in science. The answers may lead to an entirely new picture of reality, one where our universe is not the first nor the last, but one of countless cycles in an eternal cosmic rhythm. The search for a pre-Big Bang reality begins with the realization that the singularity is not physically real. It's a placeholder for ignorance, a sign that our equations are incomplete. If we can find the deeper laws that govern the universe under those extreme conditions, we might peer beyond the veil of time and glimpse the cosmos that came before ours. Several groundbreaking theories now attempt to do exactly that, each offering a different vision of what before might mean when time itself breaks down. One idea is that the Big Bang was actually a big bounce. Instead of a moment of creation from nothing, it was a rebound from a previous phase of contraction. In this view, the universe did not begin, it oscillates. As it expands, it cools. As it contracts, it heats up until reaching a critical point where quantum effects cause it to bounce outward again. Time, in such a cosmos, never truly starts or ends. Another proposal comes from Roger Penrose's conformal cyclic cosmology, which suggests that the remote future of one universe becomes the Big Bang of the next. In his elegant mathematical framework, the infinite expansion of an old universe erases all trace of scale, smoothing it into a state that is, strangely, identical to the ultra-dense beginning of a new one. Death and birth are simply different faces of the same process. Then there are string-theoretic ideas like the ekpyrotic model, which proposes that our universe was born from the collision of higher-dimensional brains floating in a vast multiverse. These collisions repeat eternally, creating cycles of expansion and contraction across dimensions we cannot perceive. Each universe inherits traces of its predecessor, not through time as we know it, but through the fabric of higher dimensional space. To grasp what these theories imply, consider the nature of time itself. We usually imagine it as a linear river flowing from past to future, but in physics time is intertwined with space. It's part of the same fabric. If space can bend, stretch and loop, perhaps time can too. What we call the beginning may simply be a bend in the timeline, a point where our definition of before ceases to apply because time curves back upon itself. In that case, the universe could be eternal yet still have a finite age from our perspective. The notion of a pre-Big Bang universe challenges not just science but philosophy. If there was something before, then creation was not creation, it was transformation. It suggests that existence is not a miracle born from nothingness, but a process governed by timeless principles. Energy, after all, cannot be created or destroyed. It only changes form. Perhaps the same is true of universes. Each cosmos could be the reincarnation of its predecessor, its energy and information recycled through the grand mechanism of reality. The search for what came before the Big Bang is not limited to equations. It also looks to the sky. The cosmic microwave background, the faint afterglow of the early universe, may carry subtle imprints from a prior epoch. Patterns in its temperature fluctuations, so-called Hawking points, proposed by Penrose could be remnants of black holes that evaporated in a previous universe. If confirmed, such evidence would be revolutionary, proving that our cosmos was not the first to exist. But even without direct proof, the logic is compelling. Every major advance in physics has come from unifying opposites, light and electricity, space and time, energy and mass. The next unification may merge existence and non-existence, showing that the universe emerges naturally from eternal cycles rather than from absolute nothingness. Still, skepticism remains. Some argue that talking about before the Big Bang is meaningless, since time itself began with the expansion. But others counter that time might be emergent, not fundamental, a property that arises only when the universe reaches a certain complexity. In that case, the question of what came before is valid, even if it requires redefining what before means. The pre-Big Bang quest also touches on our understanding of causality. In our everyday world, causes precede effects, but if time is cyclical, the universe might cause itself. The end of one cycle could give birth to the next, closing the loop of cause and effect. This self-creating cosmos defies common sense, yet it may be the most natural state of all, a universe that perpetually renews itself, without need for external intervention or ultimate beginning. The search for a pre-Big Bang reality, then, is not just about solving equations. It's about uncovering the deepest structure of existence. It challenges our most sacred assumption that there must have been a first moment. If the universe is truly eternal, then what we call the beginning is simply the latest verse in an infinite cosmic poem, written and rewritten across the ages by the laws of physics themselves. Roger Penrose, one of the most imaginative and rigorous minds in modern physics, has proposed a vision of the universe so bold that it redefines what we mean by time. His idea, known as conformal cyclic cosmology, or CC for short, suggests that the Big Bang was not the birth of the universe, but a bridge between aeons, vast epochs of cosmic history that succeed one another endlessly. In Penrose's view, the universe has no absolute beginning and no final end. Instead, it experiences a continuous sequence of expansions, each one emerging naturally from the faded remains of the previous cosmos. To grasp his vision, imagine that our universe, far into the future, continues expanding forever. Stars burn out, black holes evaporate, and matter decays until only radiation remains. Over unimaginable stretches of time, all differences between locations disappear. The universe becomes smooth, empty, and cold, a vast bath of photons travelling freely through ever-expanding space. At that stage, time itself loses meaning. There are no clocks, no processes to measure change, only pure geometry. And yet, Penrose argues, this ultimate emptiness is not the end but the beginning. Because when all mass is gone, the concept of scale becomes meaningless. Without mass, there is no distinction between large and small. In this strange condition, the infinite cold universe of the far future becomes mathematically indistinguishable from the hot, dense state at the Big Bang. By applying a special kind of geometry called conformal geometry, Penrose shows that the two extremes, the infinite future and the fiery beginning, can be mapped onto each other seamlessly. One aeon's end becomes the next aeon's birth. In his theory, the Big Bang was not a singular creation event but a smooth continuation of a previous universe after it had expanded into near-nothingness. This concept of cyclic time is unlike any other. Traditional cyclic models picture the universe bouncing between contraction and expansion. But Penrose's cycle does not require collapse. Instead, it transforms the infinite future into a new beginning through geometry alone. Time, in his model, is eternal, but divided into eras, each one lasting trillions of years, each giving rise to the next in an unending sequence. It's a universe that dies not with a bang, but with a fade, and from that silence, a new symphony begins. What makes Penrose's vision especially compelling is that it might be testable. According to his calculations, violent events near the end of a previous aeon, such as the evaporation of supermassive black holes, could leave faint imprints on the next universe's cosmic microwave background. These imprints, known as Hawking points, would appear as subtle, circular patterns in the sky, slightly warmer or cooler than their surroundings. Penrose and his collaborators claim to have found evidence of these patterns in satellite data, though the results remain controversial. If they are real, they would be the first observational proof that our universe carries the memory of one before it. Penrose's conformal cyclic cosmology stands apart from other theories because it doesn't rely on exotic physics or unobservable dimensions. It uses only well-established principles, Einstein's relativity, the behavior of radiation, and the geometry of space-time to build a coherent narrative that extends beyond the Big Bang. His genius lies in connecting two opposites, the infinitely large and the infinitely small, the frozen stillness of the far future and the explosive energy of the beginning. By erasing scale, he erases the boundary between them. Yet this idea also challenges our most basic intuitions. If time never truly begins or ends, what becomes of causality? Can one universe give rise to another without an external cause? In CCC, causation itself is cyclical. Each aeon gives birth to the next as naturally as a wave follows another on the sea. There is no first cause, no prime mover, only an eternal progression. This picture echoes ancient philosophies that saw time as circular rather than linear, yet Penrose arrives at it through pure mathematics. For him, the beauty of the universe lies in its geometry, and that geometry reveals a reality far deeper than beginnings and endings. He envisions a cosmos that continually renews itself, where the death of one universe sows the seeds of another. It's a vision of immortality written into the structure of space-time. Critics argue that CCC is speculative and that the evidence for Hawking points is inconclusive. But even skeptics admire the audacity of its simplicity. Unlike multiverse models that depend on unseen realms or infinite possibilities, Penrose's idea requires only one universe, ours repeating itself endlessly through natural laws. It suggests that eternity isn't a vast expanse of time, but a pattern of renewal, where the same fundamental geometry gives rise to countless incarnations of reality. In this cosmic symphony, each aeon is a movement, each Big Bang a crescendo leading into silence, then rebirth. If Penrose is right, the universe carries its own ancestry within its fabric, and every photon of ancient light may be a message from a previous existence. Time, in this picture, is not a line but a circle, endlessly turning. The Big Bang was not the start of everything. It was merely the latest dawn in an eternal cycle of cosmic mornings. If Roger Penrose's theory of conformal cyclic cosmology is true, then our universe carries within its oldest light the faint signatures of another cosmos that existed before ours. These are not metaphors or poetic guesses. They are potential fingerprints, subtle traces left behind by a previous aeon, encoded in the cosmic microwave background, the faint afterglow of the Big Bang. To understand what these echoes represent, we must imagine the death of a universe. Over trillions upon trillions of years, all stars burn out, galaxies fade, and black holes dominate the scene. Even those titans eventually vanish through a process called Hawking radiation, releasing their mass as tiny flashes of light before dissolving into nothing. What remains is an almost perfect void filled with radiation, so stretched by expansion that it has no energy left to interact with anything. In that state, the universe becomes scale-free. Its size no longer matters because there is no structure left to measure it against. It is at this moment, Penrose argues, that the infinite future of one universe transforms smoothly into the Big Bang of the next. But if black holes evaporated in that previous aeon, the final bursts of their energy could leave tiny imprints on the newborn universe's background radiation. These are what Penrose calls Hawking points, small circular hotspots in the cosmic microwave background where that ancient energy might have resurfaced. Detecting them is like hearing the faint echo of a voice across eons, the whisper of a world long gone. To search for these patterns, Penrose and his team analysed data from the Planck and WMAP satellites, which map the temperature of the cosmic microwave background across the entire sky. The CMB is mostly uniform, but it contains slight fluctuations, tiny differences in temperature caused by quantum variations during the universe's infancy. Hidden among those fluctuations, Penrose claimed, are small concentric circles slightly warmer than their surroundings, evenly spaced and appearing in clusters. These, he proposed, are the signatures of Hawking points, relics of supermassive black holes that evaporated in the previous cosmic cycle. According to his analysis, they appear too ordered to be random noise. However, other researchers remain skeptical. They argue that the statistical significance of these circles is weak, that similar patterns can appear by chance when analysing such complex data. Cosmology is a science where noise can easily masquerade as meaning. Yet the mere possibility of such evidence electrifies the imagination. If even one of these circular imprints is real, it would mean that our universe remembers its predecessor. It would imply that time stretches infinitely backward, that the Big Bang was not an absolute beginning, but a transition between eras. It would transform cosmology from the story of a single birth into a chronicle of eternal rebirths. The search for these echoes is not just a technical pursuit, it's an attempt to listen to the memory of the cosmos itself. The microwave background is the oldest light we can observe, released about 380,000 years after the Big Bang, when the universe first became transparent. It fills every corner of the sky, a silent sea of radiation that has travelled for nearly 14 billion years. Within its faint ripples are clues about everything that has ever happened, from the formation of galaxies to the earliest quantum fluctuations. If Penrose is right, those ripples also contain messages from before time as we know it. The idea that energy could pass from one universe to another sounds almost mystical, but it arises naturally from physics. Black holes, through their evaporation, convert mass into pure radiation. In an infinitely expanding cosmos where all matter decays, only radiation remains, and radiation, unlike matter, is unaffected by scale. It carries information forward through the conformal transformation that links one aeon to the next. The final flashes of ancient black holes may therefore light the spark of a new universe. To visualize this, imagine each universe as a single frame in an eternal film reel. The end of one frame blends into the start of the next so seamlessly that the movie never stops. It simply continues with a new scene. The energy that ends one story becomes the seed that begins another. For observers like us, trapped within a single frame, that transition looks like a beginning. The Big Bang, but from a higher perspective, it's merely continuity. The implications are staggering. If our universe carries traces of a previous one, then perhaps our own black holes will one day imprint the fabric of the next cosmos. Reality itself may be recycling through infinite epochs, each universe handing off its final light to the next generation. We may be living inside the afterglow of another civilization's sky, our stars shining in the ashes of their aeon. Even if the Hawking points remain unconfirmed, the concept reshapes how we think about beginnings and endings. The universe, once thought to emerge from nothing, may instead be a self-sustaining cycle of transformation, each phase erasing and renewing the canvas of existence. Penrose's echoes remind us that the cosmos might have memory, and that memory could stretch beyond our own universe. If future observations confirm these patterns, it will mark one of the greatest discoveries in the history of science, the proof that our universe is not the first act in the cosmic play, but just another chapter in an endless saga written across eternity. At the heart of Roger Penrose's vision lies a mathematical idea, both subtle and profound: conformal geometry. It's the key that allows him to link the infinite future of one universe with the fiery birth of the next. To most of us, geometry means shapes, angles, and distances, but conformal geometry plays by different rules. It doesn't care about size or scale, it only preserves the shape of structures, the way they stretch or bend. Two patterns can be infinitely different in size and yet conformally identical if their angles match. This is the principle that allows Penrose to bridge the gap between universes separated by unimaginable differences in scale. In our universe's far future, when all matter has decayed and only radiation remains, distances cease to have physical meaning. Without particles to define length or mass, the notion of size evaporates. Under those conditions, Penrose realized, the geometry of the universe simplifies to a purely conformal form, a realm where scaling up or down makes no difference. Now, at the opposite end of cosmic history, the Big Bang space and time are so compressed that the universe also becomes scale independent. Everything is so dense and hot that the concept of size loses meaning there as well. In both extremes, the early universe and the dying one, the same kind of geometry emerges. This symmetry is the doorway that Penrose uses to connect them. In conformal geometry, one can mathematically rescale the universe, stretching infinite distances to finite ones, or compressing infinities into points, without changing the essential structure. Penrose applied this trick to the far future of a previous aeon and discovered that, under conformal transformation, the infinite expanse of that dying universe could be mapped smoothly onto a new Big Bang. The result is an elegant mathematical bridge where time, instead of stopping, continues seamlessly into a new era. It's as if the universe passes through a mirror that turns its endless future into a new beginning. To visualize it, imagine painting a circle where one side represents the beginning and the other the end. In ordinary geometry, those points are infinitely far apart. In conformal geometry, the circle can be wrapped, so that the end touches the beginning, closing the loop. Time, under this lens, becomes cyclical, not because the universe collapses, but because scale ceases to matter. The death of one universe, infinitely stretched and diluted, becomes conformally identical to the ultra-dense birth of another. Conformal geometry thus removes the singularity problem that plagues traditional cosmology. Instead of a point where physics breaks down, Penrose's equations produce a smooth transition, a passage of geometry from one eon to the next. This approach requires no speculative dimensions or quantum fields. It's grounded purely in the mathematical structure of space-time itself. Yet its implications are breathtaking. It suggests that time may be infinite both forward and backward, that each universe gives rise to the next through a natural transformation of geometry. It also implies that entropy, the measure of disorder, resets between aeons. In the far future, when all matter decays, entropy reaches a kind of maximum equilibrium. But because there is no longer any meaningful distinction between scales, the system effectively resets to a state of low entropy again, setting the stage for a fresh arrow of time in the next universe. This solves one of cosmology's great puzzles. Why did our universe begin in such an extraordinarily low entropy state? In CCC, that orderliness is inherited from the death of the previous aeon. Conformal geometry provides the mechanism for the reset. Some critics have called this idea elegant but abstract, arguing that mathematical beauty does not guarantee physical truth. Yet history has shown that in physics, beauty often points the way forward. Einstein's field equations were once dismissed as too mathematical, and yet they reshaped our understanding of gravity. Penrose's conformal approach may play a similar role in uniting the distant past and future under one continuous framework. What makes it particularly powerful is that it avoids the need for a cosmic bounce or contraction. The universe doesn't shrink and explode, it simply continues, transformed by the rules of geometry. The Big Bang, in this picture, is not a creation event but a geometric metamorphosis, like a caterpillar becoming a butterfly. The same fabric persists, reshaped by the loss of scale. Conformal geometry, then, becomes a language for eternity. It tells us that beginnings and endings are illusions born of our limited perspective, that when the universe becomes scale-free, it enters a timeless state where the distinction between before and after dissolves. Each aeon emerges from the last, carrying faint memories in the form of radiation patterns, while erasing all trace of individual matter and structure. It is both renewal and forgetfulness written into mathematics. In this view, geometry is destiny. The curvature and scaling of spacetime don't just describe the universe, they dictate its eternal rhythm. Penrose's insight reveals that the cosmos may be its own perpetuating machine, turning itself inside out with every aeon, rebirthing without beginning or end. Conformal geometry is not just a mathematical curiosity, it's a vision of reality where time never truly starts and existence never truly stops. It is the silent symmetry beneath the cosmic dance, a symmetry that could make the universe immortal. Time, as we experience it, flows only one way from past to future. We remember yesterday, but not tomorrow. We grow older, but never younger, and broken glass never leaps back together. This directionality, this irreversible flow, is one of the deepest mysteries in physics. The equations that govern matter and energy don't care which way time runs. They work just as well forward as backward. Yet in our universe, time has a clear arrow. The reason for this, physicists say, lies in a single concept: entropy. Entropy measures disorder, or more precisely the number of ways a system's particles can be arranged without changing its overall appearance. Low entropy means order, high entropy means chaos. According to the second law of thermodynamics, entropy in a closed system always increases. Ice melts, stars burn out, structures decay, all part of the cosmic drift from order to disorder. But this raises an astonishing question. If the universe began in an incredibly hot, dense, turbulent state, shouldn't it have started with maximum entropy? Instead, it began in one of the most ordered states imaginable. This contradiction has puzzled scientists for decades. Roger Penrose has argued that this improbably low entropy beginning is the real mystery of the Big Bang, not how matter and energy appeared, but why they were arranged in such an exquisitely smooth way. Without that initial order, time itself would have no direction. The arrow of time emerges because the universe began in a state of low entropy, and has been increasing ever since. The greater the entropy, the more time seems to move forward. But why did it start that way? In a chaotic explosion, one would expect disorder, not perfection. The early universe was astonishingly uniform. So uniform that the temperature across regions separated by vast distances was nearly identical. This uniformity doesn't arise naturally from random initial conditions. It must have been encoded in the fabric of reality itself. Inflationary theory tries to explain this by proposing that a rapid expansion smoothed out irregularities, but that only pushes the question further back. What set the stage for inflation? And why was entropy so low to begin with? Penrose's conformal cyclic cosmology offers a daring solution. In his model, entropy doesn't begin low by coincidence, it resets at the end of each aeon. When the universe has expanded so far that all mass has decayed, entropy effectively loses meaning. Without massive particles to define structure, there's no difference between order and disorder. The system becomes conformally invariant, scale-free, and timeless. At that point, a new eon can begin in a pristine low-entropy state. Thus, the arrow of time is born anew with each cosmic cycle. Entropy, rather than a one-way climb toward heat death, becomes part of an eternal rhythm of reset and renewal. It's a breathtaking concept. The universe's tendency toward disorder becomes the mechanism by which it rejuvenates itself. But the relationship between entropy and time goes even deeper. In everyday experience, time seems to flow because entropy increases. Yet some physicists argue that it's the other way around, that entropy defines the flow of time itself. Without an increase in entropy, there would be no sense of before and after. Time would lose its meaning in a perfectly reversible world. That's why the heat death of the universe, when everything reaches maximum entropy, is also the death of time. In that final stillness, nothing changes, and without change, time no longer ticks. Penrose's model turns this paradox into a bridge. When time ends through the loss of all distinction, the conditions for a new beginning are born. The arrow resets, the clock restarts, and a new universe expands with fresh order. Entropy may thus be the heartbeat of eternity, pulsing with every cosmic cycle. Still, the concept of entropy is subtle. It doesn't just measure disorder, it measures information, the amount of detail needed to describe a system. In a low-entropy state, little information is needed. Everything is simple and uniform. As entropy rises, the information required increases. In that sense, the universe's evolution is also the evolution of information. Every star that forms, every life that emerges, adds to the informational richness of the cosmos. Entropy may increase, but so does complexity. From this perspective, the arrow of time is not merely decay, it's creation through transformation. The universe's march toward higher entropy allows structure, diversity, and consciousness to arise, like patterns emerging from turbulence. Yet when the process runs its course, when entropy reaches its peak, the cycle begins anew in a purified simplicity. The cosmic story is one of order giving rise to disorder, and disorder giving birth again to order. If entropy defines time, then each aeon is a lifetime of the universe itself born in order, aging through chaos, dying in equilibrium, and reborn in clarity. It's a poetic symmetry written into the laws of thermodynamics. Time, in this grand scheme, is not a straight line but a rhythm, a song composed of countless verses, each one an eon's passage from simplicity to complexity and back again. Our universe, then, may not be running out of time at all. It may simply be preparing for its next breath, waiting for entropy to dissolve the old distinctions and restore the perfect symmetry from which a new arrow can emerge. While Roger Penrose reimagined the cosmos through geometry, another group of physicists sought to rewrite it through quantum mechanics itself. Their goal was to heal the rift between the very large and the very small, to build a bridge where Einstein's smooth space-time meets the jittering uncertainty of quantum reality. From that effort arose a theory known as loop quantum gravity, and with it, a radical new vision of the beginning of the universe. Not a big bang, but a big bounce. The idea starts with the realization that space and time, according to quantum principles, cannot be infinitely divided. Just as matter is made of atoms, space itself might be made of discrete, indivisible units, a kind of atomic structure of geometry. In loop quantum gravity, space is woven from tiny loops, or spin networks, that form a dynamic, ever-changing fabric. These loops are unimaginably small, at the Planck scale about 10 feet or 35 meters, but together they create everything we know. Space is not a smooth continuum but a granular web that can stretch and twist, yet never compress to zero. That single insight changes everything about the universe's origin. When cosmologists apply this framework to the earliest moments of time, they find that as the universe contracts toward what classical physics calls the singularity, quantum effects become dominant. The loops of space resist being squeezed beyond a certain limit, just as matter resists being compressed into infinity. Instead of collapsing into a singular point, the universe reaches a minimum size, a moment of maximum density, and then rebounds. The Big Bang, in this picture, is not the birth of space-time from nothing, but the bounce from a previous contracting phase. The death of one universe gives rise to the birth of another, in a continuous cycle of expansion and contraction. The singularity vanishes. In its place stands a bridge. This big bounce elegantly solves the problem of infinities that plague general relativity. It also answers the question of what happened before the Big Bang. There was a universe before ours, governed by the same physical laws, shrinking down until quantum gravity reversed the collapse. The bounce is not a catastrophic explosion, but a smooth transition, like a heartbeat marking the rhythm of eternal cosmic cycles. Loop quantum gravity accomplishes this without invoking extra dimensions or speculative entities. It uses only known principles of quantum mechanics and relativity applied to the fabric of spacetime itself. It suggests that gravity, at the smallest scales, becomes repulsive rather than attractive, preventing total collapse. This reversal acts as the spring that propels the new expansion. The equations describing this behavior arise naturally from the quantization of Einstein's geometry. In the quantum universe, the beginning and end merge into one continuous loop, just as the name implies. What makes this idea especially powerful is that it replaces the unknowable singularity with a knowable process. The Big Bang ceases to be a mystery. It becomes a phase transition, a change in the state of the universe's geometry. Instead of asking how everything came from nothing, physicists can now explore what physical conditions led to the bounce, what patterns might survive it, and how information might pass from one universe to the next. Some versions of the theory suggest that traces of the previous contraction could be visible in the cosmic microwave background, subtle asymmetries or patterns left by the compression before the bounce. If ever detected, such evidence would confirm that our cosmos carries the memory of an earlier age. The Big Bounce model also provides a fresh perspective on time. In ordinary physics, time begins at the Big Bang. In loop quantum cosmology, time is eternal, flowing smoothly through bounces. The arrow of time may reverse near the moment of the bounce, then resume in the new expansion, meaning that each side of the bounce experiences its own forward direction. To observers in either universe, time always moves forward, but across the bridge, its flow mirrors itself. This symmetry suggests that every universe may have a twin, expanding in the opposite temporal direction. The Big Bounce thus reframes creation not as a one-time miracle, but as a natural feature of quantum geometry. It portrays the cosmos as self-renewing, free from beginnings or ends. Just as waves rise and fall without ever ceasing, universes expand and contract in an endless rhythm. This view also aligns with deep philosophical intuition, that nature abhors infinities, that nothing truly starts or stops, but transforms. The Big Bounce removes the need for something from nothing, replacing it with something from something else. It turns the singularity into a mirror reflecting the universe into itself. And because the bounce is governed by quantum laws, it may even preserve information, ensuring that no piece of reality is ever truly lost, only reshaped. In this sense, the universe could be immortal, endlessly reconfiguring its own essence through cycles of contraction and rebirth. The Big Bounce is more than a scientific hypothesis. It's a profound reimagining of existence. It tells us that creation and destruction are the same motion viewed from opposite sides, that time is a loop, and that the cosmos itself is the eternal dancer moving to the beat of quantum geometry. If the Big Bang was not a singular creation but a bounce from a previous universe, then what connects those two cosmic phases? Could there be a bridge, a quantum thread linking one reality to the next? In the vision of loop quantum cosmology and related theories, that bridge is not metaphorical but physical, woven from the same microscopic structure that underlies space-time itself. Quantum mechanics, after all, allows transitions that seem impossible from a classical point of view. Particles can tunnel through barriers, teleport information across distances, and exist in multiple states simultaneously. What if the universe itself performs a similar quantum act on a cosmic scale? In the Big Bounce scenario, as the previous universe contracts, its density and curvature increase until quantum gravity takes over. At that point, space-time becomes dominated by fluctuations, tiny quantum ripples that refuse to vanish. These fluctuations act as the scaffolding for the next universe. Instead of collapsing into a point of nothingness, the old cosmos transitions smoothly through a quantum bridge where energy, geometry, and information reorganize into a new expansion. This process is not a destruction, but a transformation, like water freezing into ice or vaporizing into steam. Each phase has its own laws, but the essence, energy, and information remains conserved. The bridge between universes is not a tunnel in space, but a phase change in the very fabric of reality. Quantum cosmology suggests that such transitions could occur naturally whenever gravity becomes strong enough to merge with quantum effects. This doesn't require divine intervention or external cause. It's built into the mathematics of existence. Some physicists have proposed that information from the old universe might even survive the passage, encoded in subtle quantum correlations. These could manifest in the new universe as faint imprints, perhaps in the cosmic microwave background, or in the values of fundamental constants. If true, every universe would inherit a kind of quantum memory, a whisper of the one that came before. In this view, reality becomes a vast evolutionary chain, each cosmos passing on information like genetic code. The constants of nature, such as the strength of gravity or the charge of the electron, might not be arbitrary, but the result of a long cosmic lineage, tuned through cycles of birth and rebirth. Our universe could therefore be the descendant of countless ancestors, each refining the parameters that allow structure, stars, and life to exist. Quantum bridges might be the mechanism through which that inheritance travels. One of the most remarkable features of quantum theory is its non-locality, the ability for correlations to persist across distances, even across boundaries. Einstein called it spooky action at a distance, yet experiments have repeatedly confirmed it. If entanglement can link particles separated by light years, perhaps it can also link phases of the cosmos separated by bounces. In such a model, the universe never truly loses connection with its past. The bridge may not be traversable in the conventional sense, but it ensures continuity of reality. This also offers a potential resolution to one of physics' most vexing paradoxes, the loss of information in black holes. According to classical general relativity, anything that falls into a black hole is lost forever, its information destroyed. Quantum mechanics forbids this. Information cannot vanish. Some researchers now believe that black holes may themselves be miniature versions of the Big Bounce A process, where matter collapses, reaches Planck-scale densities, and then tunnels into a new region of space-time. In that sense, every black hole could be the seed of a new universe, its singularity replaced by a quantum bridge. Our own universe, then, might have been born from the interior of such a black hole in another cosmos. This idea, known as black hole cosmogenesis, merges the Big Bounce concept with quantum information theory. It suggests that universes can reproduce through gravitational collapse, each carrying forward fragments of quantum data from its parent. The multiverse, under this view, is not a chaotic foam of randomness but a genealogical tree of connected realities, each linked through quantum bridges. It's a self-replicating cosmos governed by the laws of information, where existence continually spawns new forms of itself. These ideas remain speculative but are grounded in serious mathematics. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, describes the wave function of the entire universe. It reveals that time, as we know it, might not exist fundamentally. Instead, the universe is described by a timeless quantum state that contains all possible configurations. The passage from one universe to another could therefore be viewed as a reconfiguration of that wave function, a quantum transition in the grand superposition of existence. To beings like us, bound to temporal perception, that transition appears as the death of one cosmos and the birth of another. But from the quantum perspective, all universes coexist in a single, eternal state of potentiality. The bridge between them is simply a shift in probability, a reordering of the infinite possibilities encoded in the cosmic wave function. It's as though the universe breathes not in time, but in configuration space expanding and contracting through quantum transitions that have no true beginning or end. This vision transforms cosmology from a story of origins into a story of continuity. The Big Bang becomes not a singular creation but one pulse in an infinite quantum heartbeat. Every collapse gives rise to new expansion, every death to new birth, every boundary to new connection. The quantum bridge ensures that existence never breaks, it only changes form. In that sense, the universe is not a fleeting accident, but a self-sustaining cycle of transformation, a cosmic network of worlds forever linked by the invisible threads of quantum reality. For much of the 20th century, the Big Bang was seen as a single explosive event, a sudden expansion that brought the universe into existence. But in the early 1980s, a bold new idea reshaped that picture forever: cosmic inflation. It proposed that, within a fraction of a second after the Big Bang, the universe underwent an astonishing burst of exponential growth, expanding faster than the speed of light. Space itself stretched so rapidly that regions once smaller than an atom ballooned to cosmic scales. This fleeting moment of inflation solved several profound puzzles in cosmology, but it also opened a doorway to something even more astonishing: the possibility that inflation never truly ends, that our universe is just one bubble in an eternally expanding multiverse. The idea of inflation was first introduced by physicist Alan Guth, who sought to explain why the universe looks so uniform on large scales. Observations show that the temperature of the cosmic microwave background is nearly identical in every direction, even though distant regions could never have exchanged information or energy since the Big Bang. This horizon problem suggested that something must have smoothed out the universe before it became transparent. Inflation provided the answer. Before ordinary expansion began, the universe inflated so rapidly that all regions were once close enough to equilibrate, then were stretched apart to cosmic distances. Inflation also explained the universe's remarkable flatness. Without fine-tuning, general relativity predicts that space should curve strongly under the weight of its own energy. But inflation dilutes any initial curvature, just as stretching a wrinkled balloon makes its surface appear flat. Finally, inflation predicts that the universe should be filled with tiny quantum fluctuations, microscopic ripples in space-time magnified to astronomical scales. Those ripples, observed in the cosmic microwave background, later became the seeds of galaxies and clusters. Inflation not only explains what we see, it explains why we exist. Yet the mechanism that drives inflation is as mysterious as its consequences. The theory proposes a field, often called the inflaton, whose potential energy caused space to expand exponentially. When the field decayed, its energy converted into matter and radiation, reheating the universe and setting the stage for the standard Big Bang evolution. But according to quantum mechanics, fields are never perfectly uniform, they fluctuate. In some regions, the inflaton might decay quickly, ending inflation and forming a bubble universe like ours. In other regions, it could linger, allowing inflation to continue indefinitely. This realization led to a stunning conclusion. Inflation, once started, never fully stops. Somewhere in the vast expanse of space-time, new bubbles are always forming, each giving rise to its own universe with possibly different physical laws. This process, called eternal inflation, turns the cosmos into a boundless froth of creation, an ever-growing ocean of universes expanding within universes. Our observable universe, the totality of everything we can see, is just one bubble among countless others, floating in a cosmic sea that never ends. The consequences of eternal inflation are both exhilarating and unsettling. On one hand, it provides a natural mechanism for the origin of everything we know without invoking a singular creation. On the other, it raises deep philosophical questions about meaning, probability, and existence. If there are infinite universes, each with different constants of nature, then every possible outcome happens somewhere. There are versions of you in other bubbles living entirely different lives, worlds where gravity is stronger or weaker, stars never formed, or life evolved in unimaginable ways. The multiverse implied by eternal inflation is vast beyond comprehension, a cosmic infinity where all possibilities exist simultaneously. Critics argue that such a model may be untestable, that if other universes are forever beyond our horizon, their existence can never be confirmed. But some cosmologists counter that the fingerprints of inflation are already visible in our own sky. The tiny quantum fluctuations that inflation stretched to cosmic size have left patterns in the cosmic microwave background precisely as predicted. These ripples are the fossil record of inflation's quantum origins, and if inflation is eternal, then our universe is part of a self-replicating structure. forever budding new regions of reality beyond our view. Inflation also reframes the concept of time. In an eternally inflating cosmos, there is no single beginning. Different regions experience their own local Big Bangs, each marking the start of a new universe. From the larger perspective, inflation has been happening forever and will continue forever. The cosmos has no global birth, only endless creation. In that sense, inflation and Penrose's cyclic cosmology share a philosophical kinship. They both replace the singular beginning with an eternal process. Inflation just does it through expansion rather than repetition. But the idea carries a profound implication. If inflation is eternal, there was never truly a first universe. Creation is perpetual. The universe is not a one-time event, but a living process, an infinite flowering of space-time. Each bubble universe is born, grows, and cools, while new ones emerge elsewhere in the cosmic sea. The inflationary multiverse, if real, means the cosmos is not just vast, it is infinite in every sense, an unending chain of beginnings with no final end. The idea of eternal inflation stretches the imagination to its absolute limits. It tells us that creation never stopped, that our universe is merely one bubble in an infinite cosmic sea, each bubble a self-contained universe with its own laws, constants, and dimensions. What we call the universe is just our local patch of reality, a single spark in an endless fire of creation. Space itself, driven by the inflaton field, expands exponentially, and within that ever-growing expanse, tiny quantum fluctuations cause regions to stop inflating and condense into new universes. The result is a multiverse, a vast bubbling foam of universes endlessly budding from one another, each born from quantum randomness, each perhaps unaware of the rest. To visualize it, imagine boiling water. Steam bubbles form and burst in a churning sea, but the boiling never ends. Each bubble is distinct, isolated from the others by thin walls of steam, expanding and fading away while new ones constantly emerge. In the same way, cosmic inflation produces an infinite number of universes, each expanding internally while the greater space continues to inflate around them. Our universe is one of those bubbles, floating in a storm of endless creation. Inside each bubble, the local laws of physics may differ because the process that ends inflation, the decay of the inflaton field, can settle into different configurations. Some universes may have different values for the speed of light, the strength of gravity, or the mass of the electron. In others, atoms might never form, or time might behave in unfamiliar ways. The landscape of possibilities is unimaginably vast. The multiverse is not a single cosmos, but a metacosmos, an infinite ensemble of realities. Within this framework, even the concept of everything becomes relative. There is no single universe to contain all existence. Instead, existence itself is the fabric of countless universes eternally multiplying. This concept challenges not just physics but philosophy, even theology. If every possible version of events occurs somewhere, what becomes of meaning, choice, or uniqueness? In an infinite multiverse, every history unfolds somewhere, every decision is made, every life is lived in infinite variations. The notion of probability itself loses conventional sense, replaced by the sheer inevitability of possibility. Yet some scientists see beauty, not chaos, in this picture. The multiverse, they argue, provides a natural explanation for why our universe seems so finely tuned for life. The constants of nature, the precise balance of forces that allow stars, planets, and biology to exist, appear extraordinarily unlikely. If the universe were random and singular, this fine-tuning would seem miraculous. But in a multiverse of infinite variety, every possible combination of constants must exist somewhere. We find ourselves in one of the rare universes where conditions permit life simply because we couldn't exist in any other. This idea, known as the anthropic principle, turns apparent coincidence into necessity. It doesn't invoke design or purpose, only the logic of infinite diversity. Still, the multiverse idea has its critics. Some argue that it isn't science at all because it cannot be tested directly. Other universes, by definition, lie beyond our observational reach, separated from us by vast regions of still inflating space expanding faster than light. We will never communicate with them, never see their galaxies or measure their laws. To many physicists, that isolation feels like speculation disguised as theory. Yet others point out that the multiverse isn't an arbitrary invention. It's a prediction that naturally emerges from inflation, a theory already supported by strong evidence. The small-scale fluctuations inflation predicts match what we see in the cosmic microwave background with remarkable precision. If inflation is true, eternal inflation follows almost inevitably. The multiverse may therefore be a consequence of physics, not imagination. The question then becomes not whether other universes exist, but how their existence affects our understanding of reality. In a multiverse, beginning and end lose meaning. There is no single creation moment, no final fate. New universes constantly sprout as others cool and fade. Time itself becomes relative to each bubble, while the greater inflationary space continues without pause. The multiverse replaces the idea of a finite cosmos with a fractal eternity, a never-ending structure repeating at every scale. Some physicists even speculate that information might leak between universes through quantum tunneling or gravitational effects, though such possibilities remain deeply theoretical. Others wonder whether universes can collide, leaving traces in their cosmic backgrounds. If such scars were ever found, they would serve as the first physical evidence of neighbouring realities. But even without such proof, the concept transforms our sense of existence. We are no longer living in a singular universe born once and destined to die. We are inhabitants of an infinite continuum, one node in a cosmic network of endless diversity. Each universe is a verse in an eternal poem, written in the language of quantum fluctuations. To grasp this is to see creation not as a single event, but as an unending process, a cosmic tree forever branching, where every branch bears its own world. Eternal inflation paints a picture of reality that is at once humbling and magnificent, a universe that never stops creating, where even the void is alive with potential, and where existence itself is infinite in scope and meaning. To understand why eternal inflation might never end, we must explore one of the strangest ideas in quantum physics, the false vacuum. It is a concept that sounds abstract but could determine the ultimate fate of our universe. The vacuum in physics is not truly empty. It is a seething field of energy, alive with virtual particles that flicker in and out of existence. This restless background is the foundation of all quantum fields, and it possesses a certain energy level known as the vacuum energy. But just as a ball can rest in a shallow valley rather than the deepest one, the universe's vacuum may not be in its most stable state. It might be trapped in a local minimum of energy, a false vacuum. From the outside, such a state appears stable, but in truth it is precarious, always capable of collapsing into a lower energy configuration. If that collapse ever occurs, it would trigger a cataclysmic event, a bubble of true vacuum forming within the false one and expanding at nearly the speed of light, rewriting the laws of physics as it spreads. This process is called quantum tunneling, and it's one of the most mind-bending consequences of quantum theory. In the microscopic world, particles don't need to climb over barriers. They can pass through them, appearing on the other side as if by magic. This happens not through violation of physics, but because of probability. Quantum systems are governed by wave functions, and those waves sometimes extend into regions that would be forbidden in classical mechanics. The particle has a small but non-zero chance of being found beyond the barrier. The same principle can apply to the entire universe. If the vacuum we inhabit is false, then quantum fluctuations could someday allow it to tunnel into the true vacuum, creating a bubble of new physics that expands and consumes everything. The constants of nature, the particles, even the forces themselves could change within that bubble. It would be as if reality rebooted itself from scratch, replacing our universe with another governed by entirely different rules. This sounds apocalyptic, and in a sense it is. Though there's no reason to panic, the timescales involved are unimaginably long, far beyond the lifespan of any star or galaxy. But the idea has profound implications for cosmology and for inflation. In many versions of inflationary theory, the rapid expansion of space is driven by the vacuum energy of a scalar field. If that field sits in a false vacuum, inflation continues indefinitely in some regions, while ending in others through quantum tunneling. Each tunneling event produces a bubble universe where inflation stops locally, allowing matter, radiation, and galaxies to form. Meanwhile, the rest of space keeps inflating. This self-replicating process creates the eternal inflation scenario, a mechanism where new universes are constantly born from the decay of a false vacuum. It's the cosmic equivalent of boiling water, where each bubble is a new universe nucleating in an ever-expanding sea of inflating space. The quantum tunneling mechanism provides a natural explanation for how such bubbles form and why inflation never ceases globally. Every time a region tunnels to a lower energy state, inflation ends there, but the remaining false vacuum continues expanding faster than the bubbles can grow. The process never exhausts itself. In the grand picture, creation and decay occur simultaneously, forever balancing each other in a dance of expansion and renewal. What makes this concept even more fascinating is that it may not be confined to inflation alone. Some physicists speculate that our universe itself could one day tunnel into a lower vacuum state. If the Higgs field, the field responsible for giving particles their masses metastable, as some calculations suggest, then our universe is living on borrowed time. Quantum tunneling could eventually trigger a transition to a true vacuum, erasing everything we know. Yet in a deeper sense, such a catastrophe would also be a form of rebirth. The new vacuum might spawn a new universe, with new physics and perhaps new forms of life. Even destruction becomes creation on the cosmic scale. Quantum tunneling reveals that the universe is never static, never truly safe in one state. It's a dynamic entity, constantly fluctuating between possibilities, always poised on the edge of transformation. This inherent instability may be the source of eternal creation itself. The same randomness that allows particles to appear and vanish may drive the birth of universes from nothing more than vacuum energy. Through the lens of quantum mechanics, existence is not a stable structure, but a shimmering sea of potentiality. Every moment, reality could tunnel into something new. The false vacuum is thus both a threat and a promise, the mechanism that could one day end our universe, but also the force that gives rise to infinite others. It turns emptiness into the ultimate creative medium. The void is not void. It's the womb of creation. The universe, it seems, is a perpetual quantum experiment, tunneling through its own possibilities, forever rewriting the script of reality in an unending cycle of chance, change, and rebirth. When scientists tried to unite the laws of quantum mechanics with Einstein's general relativity, they encountered contradictions so deep that the entire framework of physics began to unravel. Space-time, according to relativity, is smooth and continuous, but quantum mechanics insists that on the smallest scales, nature is discrete, jittery, and uncertain. To reconcile these two realities, theorists began to imagine that perhaps our entire conception of matter and space was incomplete. Out of that quest emerged one of the most ambitious ideas in modern science string theory. At its core, string theory replaces the notion of point-like particles with tiny, vibrating strings of energy. Everything in the universe, electrons, quarks, photons, and even gravity itself, is just a different mode of vibration of these fundamental strings. The frequency and pattern of vibration determine the particle's properties, much like the tone of a note depends on the vibration of a violin string. Matter, light, and even the fabric of space-time all emerge from the same underlying symphony. Yet, for the mathematics of string theory to work, it demands something extraordinary. Additional dimensions of space beyond the three we can see. Instead of a universe with 3 dimensions of space and 1 of time, string theory requires 10 or even 11 dimensions, depending on the version. The extra dimensions are not visible because they are compactified, curled up so tightly that they exist on scales far smaller than an atom, hidden within every point of space like intricate folds within a higher dimensional origami. To visualize this, imagine a long wire stretched across a room. From a distance it appears one-dimensional, but up close, an ant crawling around it could move in 2 directions, along the wire and around its circumference. In the same way, our universe might have hidden dimensions wrapped up so small that we can't perceive them. These dimensions are not mere curiosities, they determine the physical laws of our universe. The shape and geometry of the compactified dimensions influence everything from the masses of particles to the strengths of fundamental forces. The universe we observe is just one configuration among an almost infinite number of possible shapes, known collectively as the string landscape. Each configuration corresponds to a different set of physical laws, a different universe within the greater multiverse. This idea echoes the inflationary multiverse, But now the diversity arises not from quantum randomness but from geometry itself. The hidden dimensions sculpt reality. In some versions of string theory, known as M-theory, the universe contains 11 dimensions, and our entire cosmos may be a brane, a three-dimensional surface floating within a higher dimensional space. Other branes could exist parallel to ours, each hosting its own universe. Gravity, unlike the other forces, might leak between these branes, providing a possible explanation for why it seems so weak compared to electromagnetism or the nuclear forces. In this picture, collisions between branes could even trigger new Big Bangs, birthing universes like sparks from cosmic friction. Our own universe might have been born from such a collision, an echo of higher dimensional dynamics beyond our perception. String theory also provides a framework for understanding black holes and quantum gravity. By describing how strings behave near extreme densities, it avoids the singularities that plague classical relativity. In some cases, it even counts the microscopic states of black holes, reproducing their entropy exactly as predicted by thermodynamics. This unification of gravity and quantum mechanics is one of string theory's greatest triumphs. Yet, for all its elegance, string theory remains untested. Its predictions occur at energies far beyond the reach of any experiment, and its mathematical richness makes it difficult to extract concrete answers. Some critics argue that with so many possible solutions, perhaps 10,500 different universes, the theory explains everything and therefore nothing. Others see that vastness not as a weakness but as a revelation. The physical laws we experience may be local, not universal. Our universe might simply inhabit one valley in a vast landscape of possibilities, selected by chance or by deeper principles we have yet to grasp. If the hidden dimensions of string theory are real, they might subtly influence our world. They could affect the behavior of gravity at small scales, create exotic particles detectable in future colliders, or even leave imprints in the cosmic microwave background. Some theorists have proposed that dark matter could be made of vibrations in these extra dimensions, or that the mysterious dark energy driving cosmic acceleration could be a byproduct of their geometry. Whether or not string theory ultimately proves correct, it has transformed how we think about reality. It replaces the idea of a simple universe with one of boundless complexity, where unseen dimensions weave the fabric of existence, and where geometry itself becomes the source of matter and energy. It suggests that the true architecture of reality lies hidden beneath perception, waiting to be revealed not by new eyes, but by new mathematics. In this vision, the universe is not a random assembly of particles. It's a cosmic instrument, tuned by invisible dimensions resonating with the music of creation. If string theory is the grand symphony of creation, then brain cosmology is one of its most dramatic movements, a vision in which entire universes drift, like colossal membranes through higher dimensional space, occasionally colliding in cosmic cataclysms that give birth to new realities. In this framework, our universe is not the totality of existence, but a three-dimensional brain floating within a higher dimensional arena called the bulk. Everything we know, galaxies, stars, atoms, even light itself is confined to this brain, unable to escape its surface. Only gravity, the most elusive of the fundamental forces, can move freely through the bulk, linking our universe to others that might exist parallel to it. This concept, known as the brain world scenario, transforms the universe into a dynamic landscape of membranes that stretch, ripple, and interact across hidden dimensions. In this higher dimensional reality, multiple brains can coexist, each hosting its own universe with its own version of physics. The bulk becomes a cosmic ocean, and brains are its drifting continents. One of the most provocative versions of this idea is the ekpyrotic or cyclic universe model, proposed by Paul Steinhardt and Neil Turok. They suggested that the Big Bang was not the beginning of time, but the result of a collision between two brains in the higher dimensional bulk. When these immense membranes approach each other, their mutual attraction intensifies until they finally collide, releasing colossal amounts of energy that manifest as a burst of matter and radiation, the birth of a universe. Afterward, the brains rebound, drift apart, and over immense spans of time, the cycle begins again. In this model, the universe experiences repeated phases of expansion and contraction, with each collision igniting a new Big Bang. The process could continue indefinitely, making the cosmos an eternal engine of renewal. the brain collision model elegantly sidesteps the problem of the singularity. Instead of a point of infinite density, the universe's origin becomes a geometric event, a clash of higher dimensional surfaces. Space and time do not break down, they transform. The energy of the collision reheats the brain, creating the hot plasma from which stars and galaxies eventually emerge. This perspective also offers explanations for several cosmological puzzles. The uniformity of the cosmic microwave background, for instance, could result from the evenness of the brain collision, which spreads energy uniformly across space. The slight irregularities that seeded galaxies might correspond to ripples in the brains themselves, imprinted during their approach. Even the mysterious dark energy accelerating our universe's expansion might be the influence of another brain tugging subtly on ours from across the fifth dimension. To imagine this, picture two vast flexible sheets suspended in invisible space. Each represents a universe. They ripple with waves of gravity, drift slowly toward each other, and when they finally meet, the impact releases energy equivalent to 1 trillion supernovae. To inhabitants living within one of those sheets, that event would appear as a Big Bang, a sudden explosion of light and matter seemingly from nothing. Yet to an observer in the higher dimensional bulk, it is simply a collision, a cosmic heartbeat in an eternal rhythm of approach and retreat. The ekpyrotic scenario draws deeply from both string theory and relativity, weaving them into a unified story of cyclical creation. But it also connects with ancient philosophical ideas of eternal return, the notion that the universe undergoes infinite cycles of death and rebirth. Here, though, myth becomes mathematics. The brain collisions follow equations, not legends, yet their poetry remains. In this vision, time has no beginning and no final end, only an unending sequence of expansions, coolings, and rebirths. Each aeon inherits subtle traces of the previous one, perhaps in the form of gravitational waves echoing through the bulk, or in the curvature of cosmic space itself. The bulk, though invisible to us, could be the true stage of cosmic history, where the drama of existence plays out in dimensions beyond imagination. Some scientists have even speculated that the bulk could contain countless brains, each a separate universe unaware of the others. The gravitational influence between them could explain why gravity in our universe is so weak, it leaks into the higher dimensional bulk. This leakage might also produce detectable signatures, such as tiny deviations in the inverse square law of gravity, or specific patterns in cosmic background radiation. Detecting such evidence would revolutionize physics, confirming that our universe is but one surface in a vast multidimensional ocean. The brain-world theory thus offers both scientific and philosophical wonder. It tells us that what we perceive as empty space may be teeming with unseen realities just beyond our dimensional reach, that every atom, every star, every thought exists on a fragile membrane floating through eternity. The collisions that create universes are not random disasters but acts of cosmic renewal. In this grand framework, the Big Bang was not a singular beginning, but part of an infinite cycle of creation driven by the elegant geometry of higher dimensions. The universe becomes not a lone story, but a symphony of brains rising, falling, colliding, and rebirthing worlds in an endless dance through the hidden corridors of reality. For centuries, humanity believed it had uncovered the essence of the cosmos. Newton revealed gravity's universal pull, Einstein bent space and time, and modern physics dissected matter into its smallest components. Yet, as the 20th century ended, astronomers made a staggering discovery. Everything we can see, stars, planets, gas, dust, all the atoms that make up the known world accounts for less than 5% of the universe. The remaining 95% is invisible, untouchable, and utterly mysterious. This unseen majority is what scientists now call the dark universe, composed of two elusive ingredients, dark matter and dark energy. They are not simply gaps in our understanding, they are the dominant architects of cosmic reality. Dark matter reveals itself through gravity's whisper. When astronomers observed galaxies, they noticed something impossible. Stars near the outer edges were moving far too fast. By Newton's laws, they should have flown away into space, yet they remained bound. The only explanation was that an unseen mass surrounded each galaxy, exerting a gravitational pull strong enough to hold everything together. This invisible halo of matter outweighs all visible stars combined. It doesn't emit light, absorb it, or interact with radiation in any known way. It's as if galaxies swim in vast, transparent cocoons of shadow. Dark matter also shapes the universe on the grandest scales. When scientists mapped the distribution of galaxies, they discovered a cosmic web, a network of filaments and voids stretching across billions of light years. Dark matter forms the scaffolding of this structure, pulling ordinary matter into clusters where galaxies ignite like lanterns on invisible threads. Without dark matter's gravitational influence, the universe would have remained a featureless fog, never forming stars, planets, or life. Yet despite decades of searching, no one has directly detected a single dark matter particle. Candidates abound, weakly interacting massive particles, WIMPs, sterile neutrinos, axions, or even primordial black holes, each a different shadow cast by theory. Deep underground detectors wait patiently, shielded from cosmic rays, hoping for a faint signal, a tiny recoil as a dark matter particle brushes an atom. So far, the silence endures. Still, the evidence of dark matter's existence is overwhelming, etched into the motion of galaxies, the bending of light by gravity, and the echo of the Big Bang itself. If dark matter is the cosmic skeleton, dark energy is the force that animates it. Its discovery was perhaps even more shocking. In the late 1990s, two independent teams studying distant supernovae found that the expansion of the universe is not slowing down as expected, it is accelerating. Some unknown energy, permeating all of space, is pushing galaxies apart faster and faster. This mysterious pressure accounts for about 70% of the total energy of the cosmos. Dark energy is not like any form of matter we know. It doesn't clump or dilute. It remains constant even as the universe expands. Its nature is still an enigma. It could be the energy of the vacuum itself, a cosmological constant as Einstein once proposed. Or it could be a dynamic field that changes over time, a phantom force woven into the very fabric of space-time. Whatever it is, it dominates the evolution of the cosmos. In billions of years, as dark energy continues to accelerate expansion, distant galaxies will drift beyond our observable horizon, their light forever unreachable. The universe will grow vast and lonely, with only local clusters remaining bound by gravity. The stars will fade, and the cosmic web will dissolve into darkness. This is the quiet tyranny of dark energy, a force that stretches the universe apart, perhaps forever. Together, dark matter and dark energy form the invisible web that defines reality. They determine the universe's structure, shape its destiny, and yet remain utterly mysterious. Every observation we make is filtered through their unseen influence. We are like fish studying the currents of an ocean we cannot see, aware only of its effects. Some physicists believe that dark matter and dark energy might be connected. Two aspects of a deeper cosmic field. Others suspect that our understanding of gravity itself may be incomplete, that Einstein's equations might need modification on cosmic scales. Perhaps what we call dark is not missing matter or energy at all, but a misunderstanding of spacetime's true geometry. Regardless, the dark universe reminds us that our knowledge is still young. The cosmos we can observe with telescopes and detectors is just a flickering candle in an ocean of shadow. And yet, it is within that shadow that the future of cosmology lies. New instruments, like the James Webb Space Telescope and the upcoming Euclid mission, will map the dark matter distribution and measure the subtle distortions caused by dark energy's push. Each observation brings us closer to unveiling the hidden architecture of the universe. In the end, the dark universe teaches us humility. What we see is only the surface of a deeper reality. Beneath every star shines an invisible structure of gravity and energy, holding the cosmos together and driving it apart. The night sky, once thought to be filled with light, turns out to be mostly darkness. But within that darkness lies the true heartbeat of creation. Every story, no matter how vast, demands an ending. And so cosmologists have long asked what the final act of the universe will be. Will everything fade into eternal stillness, collapse into fire, or transform into something new? The answer depends on the balance between gravity, dark energy, and time itself. For decades, scientists envisioned three main possibilities: the Big Crunch, the Big Freeze, and the Big Rip. But as our understanding deepened, a more haunting question emerged. Could death itself be just another beginning? The universe's fate begins with its expansion. Ever since the Big Bang, space has been stretching, carrying galaxies away from one another like dots on an inflating balloon. For billions of years, gravity worked to slow that expansion, its invisible hand pulling matter together. But in the late 20th century, astronomers discovered that instead of slowing down, the expansion was speeding up, driven by the mysterious force of dark energy. That revelation transformed our vision of the future. If dark energy remains constant, it will dominate forever, pushing galaxies apart at an ever-accelerating rate. Eventually, distant galaxies will vanish beyond our cosmic horizon, their light red-shifted into oblivion. Only the nearest clusters bound together by gravity will remain visible. Over trillions of years, those too will fade. Stars will burn out one by one, leaving behind white dwarfs, neutron stars, and black holes. New stars will cease to form as the raw gas needed to create them becomes exhausted. The cosmos will enter its twilight. This scenario is called the heat death, or the big freeze. It is not an explosion or a collapse, but a slow, irreversible fading of energy gradients, the cosmic equivalent of embers cooling after a fire. Entropy, the measure of disorder, will reach its maximum. When everything has the same temperature, no work can be done, no structure can form, no life can exist. Even black holes, the last remaining beacons of structure, will slowly evaporate through Hawking radiation, shrinking and fading into nothing over unimaginable timescales. The universe will become a dark, cold expanse of thin radiation and elementary particles drifting endlessly through an empty void. Time itself will lose meaning, for in a perfectly static state, nothing changes. Yet not all endings are so final. Some cosmologists envision a more violent conclusion, the Big Rip. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even atoms. First, clusters of galaxies would dissolve, then solar systems, then molecules, and finally the very fabric of space-time itself would rupture. In this scenario, the universe ends not in quiet decay but in a catastrophic disintegration, a cosmic unravelling where existence itself is pulled apart by the accelerating expansion. But there are other, more hopeful visions. Some physicists believe the universe may one day reverse its expansion. If dark energy changes sign or weakens, gravity could regain dominance, pulling the cosmos back together into a colossal contraction, the Big Crunch. Galaxies would collide, stars would merge, and temperatures would soar as everything collapses into a final inferno. In classical cosmology, that collapse would end in a singularity, but in quantum cosmology, it could trigger a bouncer transition to a new expanding phase, a new universe born from the ashes of the old. This is the cyclic or oscillating universe, where every death is followed by rebirth. It resonates with the ideas of Roger Penrose's conformal cyclic cosmology and the big bounce of quantum gravity. In both visions, the end of one universe becomes the seed of the next. The heat death may not be a permanent grave, but a transformation into a new state of order. When matter decays and black holes evaporate, only radiation remains, and in that radiation lies the possibility of renewal. As Penrose proposed, when the universe becomes completely scale-free, when distances lose meaning, the geometry of space-time resets, birthing a new cosmic aeon. In that sense, even entropy's victory is temporary. The cosmos may rise again, not from collapse, but from dissolution. Beyond physics, these possibilities evoke profound philosophical reflection. If the universe can renew itself, then perhaps nothing truly ends. Existence becomes an eternal cycle of transformation. If instead it fades forever, then meaning must be found within the fleeting spark of order we now inhabit. Either way, the fate of the universe reflects the laws that govern it: balance, change, impermanence. On the human scale, these timescales are unimaginable. The end will not come in fire or noise, but in silence so vast it defies comprehension. Yet even then, the laws of physics endure, carrying the memory of everything that was. Whether the cosmos freezes, rips, or renews, it remains bound by the same mathematical elegance that shaped its birth. Perhaps, in the ultimate stillness, the universe does not die. It merely waits, ready to awaken again in a new form, as it has countless times before. Imagine for a moment that everything you see, the stars in the sky, the the people around you, even your own thoughts, might not be as three-dimensional as they seem. Imagine that the universe itself could be a vast illusion, a hologram projected from a deeper, lower-dimensional reality. This is not science fiction, but one of the most profound ideas in modern physics, the holographic principle. It suggests that all the information contained in a region of space, everything that happens within it, can be described entirely by data encoded on its boundary. In other words, the universe could be like a cosmic movie projected from the edge of reality, where our three-dimensional world is a kind of shadow cast by deeper physics occurring on a two-dimensional surface. The origins of this idea trace back to the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something remarkable: the entropy of a black hole. The measure of how much information it contains is proportional not to its volume, but to the area of its event horizon, the boundary beyond which nothing can escape. This discovery shocked physicists because it defied ordinary intuition. Normally, the amount of information a system can hold scales with its volume, like the number of books you can fit in a library. But black holes seem to follow a different rule, where the information content is encoded on a surface, not inside it. That insight led to a radical generalization. If black holes obey this rule, perhaps the entire universe does. The universe itself might be a holographic system where the physics inside a region is completely determined by information inscribed on its boundary. The idea was later refined through string theory, particularly in the famous AD-CFT correspondence proposed by Juan Maldacena in 1997. He showed that a universe described by gravity in a higher dimensional space, anti-de Sitter space, can be exactly equivalent to a quantum field theory without gravity on its lower dimensional boundary. Two completely different descriptions, one in bulk space-time, one on a flat surface turn out to contain the same information. Gravity and quantum mechanics, once thought irreconcilable, become two sides of the same holographic coin. This principle has transformed theoretical physics. It suggests that space itself might be emergent, not fundamental, construct arising from deeper informational relationships. Just as a holographic image appears three-dimensional, though it's encoded on a flat plate, the geometry of space-time might emerge from the entanglement patterns of quantum information stored on cosmic boundaries. In that sense, reality as we experience it could be a vast data structure, with gravity and geometry arising from information flow. The holographic principle also offers new perspectives on the black hole information paradox. If information about everything that falls into a black hole is preserved on its event horizon, then nothing is truly lost, it's simply transformed. The universe, at its core, becomes an information-conserving system. This concept dovetails beautifully with quantum mechanics, which demands that information can never be destroyed. The holographic model resolves the tension between the apparent loss of information in black holes and the unbreakable laws of quantum theory. But the implications go far beyond black holes. If the holographic principle applies universally, then every region of space, including our own universe, might be governed by this boundary encoding. Some physicists believe our entire cosmos could be described by data written on a distant cosmic horizon, the edge of the observable universe. Everything we see and feel would then be a projection from that boundary. Even time might emerge from the evolution of that encoded information. The deeper we look, the more reality seems to behave like a computational system processing data according to fundamental rules. Some theorists, like Leonard Susskind, have taken this even further, proposing that quantum entanglement, the mysterious connection between particles, is the glue that holds space-time together. In this view, the fabric of the universe is woven not from matter or energy, but from relationships, from the correlations between bits of information. Space exists because things are entangled. The strength of those connections determines the curvature of space and the presence of gravity itself. If that's true, then the universe is not a stage on which matter acts. It is the result of information acting upon itself. The holographic principle thus dissolves the boundary between physics and information theory, between existence and computation. It suggests that what we call reality is a projection of deeper informational laws, that every particle and wave is a pixel in a vast cosmic code. Philosophically, this idea blurs the line between objective and simulated worlds. If the universe is fundamentally informational, then the distinction between real and virtual may be one of scale, not substance. Reality becomes a kind of cosmic computation unfolding across dimensions, where consciousness itself might be a reflection of the universe's informational architecture. Whether or not the holographic principle proves literal, it reshapes our understanding of existence. It tells us that reality may not be built from things, but from information about things. The universe, then, is not merely a place. It's a story being written on the boundary of eternity, a holographic masterpiece where space, time, and life are the patterns emerging from the endless flow of information. As we reach the end of this journey through cosmic time, a question emerges that no equation can ignore. What role does consciousness play in the story of the universe? For all our talk of matter, energy, and geometry, there remains this undeniable fact. The cosmos is aware of itself through us. We are not passive observers standing outside creation. We are its living expression, the eyes and mind through which it contemplates its own existence. The story of the universe is, in the deeper sense, also the story of awareness awakening from the void. For billions of years after the Big Bang, the universe was a vast and unconscious expanse of radiation and matter, forming galaxies, stars, and planets. Then, on one tiny world circling an ordinary star, atoms learned to think. From the chemistry of carbon arose consciousness, a phenomenon that seems to defy the reductionist logic of physics, yet flows naturally from it. The same laws that govern the dance of galaxies also shape the neurons in our brains. Somehow, from the interplay of matter and energy, the universe has generated beings capable of reflection, imagination, and wonder. That realization changes everything. It means the universe is not merely a stage for blind processes, but an unfolding that includes awareness as one of its fundamental outcomes. Life, far from being an accident, may be the mechanism through which the cosmos experiences itself. Every act of perception, every spark of thought, is a point where the universe turns inward to witness its own form. Some thinkers, both ancient and modern, have suggested that consciousness might not simply arise from matter, but be woven into the fabric of reality itself. In certain interpretations of quantum mechanics, the act of observation plays a crucial role in determining physical outcomes. The observer, far from being irrelevant, is an active participant in shaping what is real. If that's true, then consciousness and the cosmos are entangled in a feedback loop, each defining the other. The universe gives rise to conscious beings, and consciousness in turn helps bring the universe into definition. This idea, once confined to philosophy, now finds echoes in the frontier of science. The holographic principle and quantum information theory both suggest that information, not matter, is the fundamental substance of reality. If consciousness is what processes information, then perhaps mind and cosmos are not separate but two aspects of the same underlying field. Panpsychism, an idea once dismissed as mystical, is re-emerging as a serious proposal. That consciousness, in some primitive form, exists throughout the universe, in every particle, in every vibration of space-time. Under this view, the difference between atoms and humans is not the presence of consciousness, but its degree of complexity. The universe becomes a vast hierarchy of awareness, from the faint stirrings of quantum systems to the self-reflective minds capable of asking why. The more complex the organization of information, the more intense the experience of being. This continuity transforms our relationship with existence. It tells us that the universe is not a cold, indifferent machine, but a living process, an unfolding consciousness exploring itself through form and transformation. From stars forging elements to minds forging meaning, the cosmos evolves from simplicity to awareness, from matter to mind. In that sense, consciousness is not an anomaly, it is the culmination of the universe's creative arc. The laws of physics gave rise to complexity. Complexity gave rise to life, and life gave rise to thought. And through thought, the universe contemplates its own origins and destiny. The poet Teilhard de Chardin called this the omega point, the moment when consciousness and cosmos converge, when evolution realizes itself as self-awareness. Whether that moment lies in the future or is unfolding now within us, it signifies that the cosmos is not finished. Its evolution continues through the growth of awareness. Our intelligence, our creativity, our ability to dream and build all are extensions of the same cosmic impulse that flared into existence 14 billion years ago. We are the Big Bang thinking about itself, the echo of that first light still questioning its purpose. Yet with awareness comes responsibility. If consciousness is the universe reflecting on itself, then how we act, think, and create shapes that reflection. The story of the cosmos is no longer just about stars and galaxies, it's about meaning, empathy, and stewardship. The same forces that gave rise to us can destroy us if we forget our place in the grand design. But if we embrace our role as co-authors of reality, then perhaps we can guide the next chapter of cosmic evolution, not through conquest, but through understanding. In the end, the boundaries between science, philosophy, and spirituality dissolve. The universe is not a machine to be observed, but a living mystery to be experienced. Its ultimate truth may not be found in equations or telescopes, but in the simple awareness of being. When we gaze into the night sky and feel that quiet sense of awe, it is the universe remembering itself. Every heartbeat, every breath, every spark of thought is part of the same infinite rhythm. The cosmos is not elsewhere, it is within us, looking out through our eyes, dreaming its own eternal dream of existence,